Kia ora koutou. This vectors question is a request from Theo, and it's from last year's June papers, and it's paper 32. And I did this question and I really, really like it, but I think it's one of those ones where the hardest part is in the first bit, and then once you get that worked out, then B and C are actually a really easy 6 marks. But part A is not difficult, but it's a little bit different. And when you read the examiner's report, that's exactly what they say, that candidates found that it's easy to get bogged down with a little bit of what is really year 11 algebra, but there are a lot of variables floating around, which you'll see when we go through it. Okay, so we've got 2 lines and they've got these vector equations. This is the first one and this is the second one. So obviously we're going to start by putting those into column or into column form. You can see that this one's pretty normal. It's just got numbers and it's got a parameter lambda. This one's got parameter alpha, but the direction vector has got 2 unknown things in it. It's got A and B and then 1 here. So the first thing that we have to do is, given that those 2 lines intersect, we have to show that this is true. And that sounds pretty innocuous, but it just means we've got 4 things floating around, right? We've got lambda, mu, and then A and B. So an obvious strategy is to try and reduce the number of floating things or variables. So I'm going to start by eliminating one thing in there. And I think it doesn't really matter what you pick as long as you have that strategy that you're going to reduce the number of variables down. And then once we've done that, then part B says, given that those lines are perpendicular, we have to figure out what A and B are. As soon as you see the words perpendicular, you should be thinking about using the scalar product and setting that equal to 0. Now, when I did this question, it felt so easy for 4 marks that I kind of wondered if I'd missed something, but I hadn't. And then the last part says that when A and B have got these values, we have to find the position vector of that point of intersection. So you can think of this question as going like this. In the first part, we've got 2 lines. We've got line L and line M. And we have to show that if they're going to intersect, that there has to be, the relationship between A and B has got to be 4 is equal to 2B minus A. And then in the second part, we're told that not just do they intersect, but that where they intersect, the angle formed E, something bad just happened, the angle formed is a right angle. I'll just turn off that ink to shape. Sorry about that. Okay, so just in the second part, we're showing that the intersection is going to give me a scalar product of 0, right? Because we know that if theta is the angle formed where the lines intersect, that's going to come from this vector dot product with this one, blah, 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 right? So if it's a 90-degree angle, cos of theta is equal to 0. So all we have to worry about is the dot product. We don't even have to work with the magnitudes. And then the last part of the question is to say, well, now that we know that there's an intersection point, find me the position vector of that intersection point. So that's a lot of lead-in, more than usual, for this question, because now I'm just going to get into working my way through the algebra. So Theo didn't need me to do the first part, but that's probably the bit that I'm going to take the most time on. Keep sending your questions in. I've got another request from Ben for a stats one, but that's about all, and I should get a little bit of time later on tonight or tomorrow. So let's just start by putting this all into component form. So try and do this before I do this. Pause the video and have a go. So for for line L, I got R is equal to -1, 3, 4, plus lambda times 2, -1, -1. And then for the second line, line M, we can write it as 5, 4, 3, plus mu times A, B, and 1. So if they intersect, then we know that there has to be a set of lambda and mu values that make all 3 of these equations true. So if we write those first 2 out, we see that we've got A, B, lambda, and mu. But when we write out the third one, we've got 4 minus lambda is equal to 3 plus mu. So I decided that this was a good enough place to start eliminating. And that means that I can write, let's see, well, I've got mu here, so I'm going to make mu the subject, and I'll get 1 minus lambda is equal to mu. Okay, so, and that's if they intersect. what I can do now is that I can take this back to these equations here and replace mu with 1 minus lambda. Okay, so that's the next thing that I'm going to do. Just shrinking that down a wee bit. We get -1. Let's just do some labelling. That's equation 1 and that's equation 2. -1 plus 2 lambda is equal to 5 plus a times 1 minus lambda. And 3 minus lambda is equal to 4 plus b times 1 minus lambda. Now, let's just clean up everything here. So this is still equation 1, and this is equation 2. Right, so equation 1 is going to give me what? Well, just think about where I'm going to go with this. In this equation, I've got lambda in A, and in this equation, I've got lambda in B. So I'm going to get an expression for lambda in terms of A here, and I'm going to get an expression for lambda in terms of B here. So in this one, I'm going to get lambda equals blah, 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 and in this one, I'm going to get lambda equals blah, blah, blah. And if everything's working, if there's an intersection, those two lambdas have got to be the same. In other words, I'm going to take each equation, muck around with it, and make lambda the subject. So working with equation 1, we've got -1 plus 2 lambda is equal to 5 plus a minus a lambda. Get everything with lambda onto one side. So we have 2 lambda plus a lambda is equal to 5 plus 1 plus a. That gives me lambda into 2 plus a is equal to 6 plus a. So lambda in terms of a is given by this. Right, now we're going to do the same thing with the second equation. We've got 3 minus lambda is equal to 4 plus b minus b lambda. Right, that's just expanding out this side. Now I'm going to gather up the lambda terms. I get negative lambda plus b lambda here on this side, and I get 4 plus b take away 3. That gives me lambda into b minus 1 is equal to 1 plus b. So now we get lambda is equal to 1 plus b over b minus 1. Right, now what can I do? Well, I'm just about there, right? Because I've got lambda is equal to this and lambda is equal to this. That's if they intersect. So 6 plus a over 2 plus a has to equal 1 plus b over b take away 1. Cross multiplying everything gives me 6 plus a times b take away 1 is equal to 1 plus b times 2 plus a. And a whole lot of stuff's going to disappear. 6b plus ab minus 6 minus a is equal to 2 plus 2b plus a plus ab. The ab's go away, and then I've got, let's see, 6b minus 6 minus a is equal to 2 plus 2b plus a. I'm going quite slowly because I know that I've gone this far. I really don't want to muck this up. So here we have 4b here is equal to 2 plus 6, which gives me 8. And I've got a plus another a plus 2a. And that gives me 2b is equal to 4 plus a. And the result that we wanted was that 4 is equal to 2b minus a. Now that was a lot of work for those 4 marks, but now watch how easy it's going to get from here. So let's go back to the question. Given also that they're perpendicular, find the values of a and b. Right, so now we're going to work with the direction vectors. So if L and M are perpendicular, then we've got the direction vectors. So let's just draw a picture. Here's L, and here's M, and here's theta. Then the direction vectors are given by 2, -1, -1, and 2b minus 4, b, and 1. And that's because a is equal to 2b minus 4. Okay, so that lets me substitute that into there. And so we know that that scalar product is equal to 0 since cos of theta is equal to the direction vector for L and the direction vector for M scaled. And that has to equal 0. So we get a very simple linear equation here. Right, for this one here, we get 4b minus 8 minus b minus 1 equals 0, giving me 3b equals 9. Oh, we're running into that earlier question. 3b equals 9, so b is equal to 3. And we know that a is equal to, what was a equal to? Let's have a look, hang on. Let's just back up. Oh, a is equal to 2b minus 4. So a is equal to 6 minus 4, which is equal to 2. Okay, so we've got a is 2, and we've got b as 3. So that's the second 4 marks, believe it or not. Lastly, we're asked to figure out what the position vector of the point of intersection of L and M is. But remember, all the way back at the start when we did this work, I'm just going to get rid of some of this working here. So if you've set your work out logically, hopefully what you'll see is that we got this equation for mu, right? So mu was 6 plus a over 2 plus a. Sorry, not mu, lambda. And it was also equal to this. So we can take either one of these, and that's going to give me the value for lambda. And we worked out very early the link between lambda and mu. So using that first one, lambda is going to be 6 plus 2 over 2 plus 2, which is 8 over 4. So lambda is equal to 2. And that means that 1 minus 2 is equal to mu. So that one is coming from there. So lambda is equal to 2. Actually, I don't think I need both of them, do I? I just need one of them. Right, so from lambda equals 2, I can take this and I can pop it back in my very first equation because that's going to give me the position vector. Right, so working in here, we can work with line L, and we know that that intersection point is going to be at lambda equals 2. So the very last thing we've got to do is to substitute that in. Negative 1, 3, 4 plus 2 times 2, negative 1 gives me the position vector negative 1 plus 4, 3 minus 2, and 4 minus 2. So we'll call that OP 3, 1, and 2. Now we were given those equations in component form, so I'd like to write it back in component form at the end. So it's equal to 3i plus j plus 2k. Right, so there you go. Theo, that was a great question. Thanks very much for sending it in. And Ben, I will do your one later on tonight.